All right, this is a worksheet that I gave y'all yesterday. This is just the back side that we were working on. I know we left one of the problems on the front blank. We're going to go back and we'll do that later. But I want to focus on, again, being able to solve for a limiting reactant problem. Now, we're not going to do it the exact way that they're going to do it. We're going to do it a little bit different. We're going to kind of skip around. So, the first thing that we're going to have to do, what's wrong? I know, that's what I just said. I know I left one blank. I just said it. This is 2 days in a row that you haven't listened to the words that come out of my mouth. Okay? So, which of the reagents, again, we don't like the word reagent, is a reactant? And B, this is the part we're going to change a little bit. It says, what is the maximum amount? Now, what does maximum mean? The most. So if I gave you all these ingredients to go make me cookies, how would you explain what is the maximum amount of? This is how many cookies you can make, right? If I give you all these ingredients where you know you need so many cups of sugar, so many eggs, so many cups of flour, so many things of whatever all those cookie things need, and so you can determine exactly how many cookies can be made from your amount of products. Guys, put your iPads up. You don't need it. Okay? And then, we're not going to get to this today, but we'll talk about this later. How much of the other reactant is left over. But we can go ahead and put this by letter C. This is the excess. How much excess is left over. So, do you agree if I gave you all these random amounts of ingredients, would you eventually run out of one of them first? And then you would have so much left over of other things, okay? So that would be the excess. And then we're going to talk about percent yield. Go ahead and do this. Write this, and I'll explain every bit of it later. Percent Y, which stands for percent yield, is actual divided by, and this is a big long word, theoretical times 100. And I'll explain every bit of that later, but I want you to go ahead and have it. Actual divided by theoretical times 100. I know you don't know what any of that means. You won't, but you will later. Okay? Now, again, to work any stoichiometry problem, a minimum is a percent Y. Percent Y stands for percent yield. Yes. Yep. All of that times 100. So basically the fraction times 100. Okay. So let's go ahead and look at problem number 1. We've got a, matter of fact, I'm just going to erase this and go ahead and slide it up. I meant to talk about this. I didn't even finish point B. What is the maximum amount of each product? We're actually going to kind of scratch out the word each, and I'm just going to pick one random one and determine the max amount of product that can be formed. And I'm going to pick one of the products, just so we don't have to do both of them. Okay? All right, so problem number 1. To do any stoichiometry problem, it must be, take 2 seconds and see if you can bounce that. Please don't say it out loud. Let everyone have a chance to attempt. Get 1113. Oh, duh. What am I doing? Sorry, forgot the first 3. It's not as easy as I thought it was. Alright. Answer the questions above. We've already talked about that. Assuming that we started with 30 grams of ammonium nitrate, which compound up here is ammonium nitrate? The first one. So I've got 30. Now I'm going to add a decimal. What does adding that decimal make it do? Go to 2 sig figs, okay? Assume that we have 30 grams of ammonium nitrate and 50 grams of sodium phosphate. What's sodium phosphate? Very good. So we're going to say 50 grams of sodium phosphate. Now notice they don't mention anything about the product, but the first part says answer the questions above. So I'm just going to pick one random one. We're going to go to the easier compound. What's the easier product? Over there will look simpler. Alright, well, let's go with the simple one first. So we're going to go with how many grams of sodium nitrate can be formed. Alright, so here's the deal. And this is what all limiting reactant problems have the problem with. Which one of those 50 or 30 do I start with to try to convert to the other side? Do I choose the 30 because it's less? No. Yesterday, flip back over the very top. You wrote two things. Number one, you wrote that the limiting reactant runs out first, and number two, what did you write? You can't compare grams to grams. So that's our problem. So you also wrote steps down, and I'm going to rewrite these steps today. All right, so steps, ignore the orange. I don't know why that happened. Step number one is we're going to go gram to mole. Step two, we're going to go moles. And how did y'all write it? Moles of given to moles of unknown. Is that what y'all wrote? Oh, that's right. Moles of reactants to moles of unknown. I can't remember exactly how I said it yesterday. And then finally, the easy step is number three. The LR is the least number. Now, and again, I kind of want to add this. Remember, this must be a reactant, because what does LR stand for? So I'll put your iPad up, please, the second time. Mackenzie, put yours up as well, on the floor. Okay. What does LR stand for? Limiting reactant. It must be a reactant. Okay, so that's going to be the key there. All right, so let's go back. The first thing. Sure did. All right, so let's just go ahead and start setting it up. So I've got 30 point, nope, not 0.0. It's just point. 30 grams of NH4NO3. Make sure you kind of conserve your space. Don't go wide with these. I know these compounds are long, but do the best you can. NH4NO3, and then moles of NH4NO3. We're going to do it again. Most of the compounds I'll ever give you will not be this long and complicated. 50 grams of Na3PO4. Logan, do me a huge favor. Will you see if my blue calculator's back out there? I brought it in. And I can run these. Is it? Okay. So I've got grams of Na3PO4, moles of Na3PO4. Okay, now, this is the easy part. What does mole get because it's with grams? Give it a 1, and mole gets a 1 here on the bottom. So let's run these masses real quick. Please don't have this. Batteries are low. Alright, so I've got 14.01 times 2 plus 4.04 plus 16 times 3 gives me a total mass of 80.06. 80.06, and then the bottom one is 22.99 times 3 plus phosphorus is 30.97 plus 16 times 4 gives me a grand total of 163.94. So those are my masses. Now I've done the hard part for you. I've given you the masses. Run the moles for me. Give everybody a chance to do it. Please. Think you got them? You have them? What's the top one? Say that again? Oh, I thought you said 137. I said, ooh, okay. 0.37 moles. Now I'm going to leave off the other compound because I don't honestly feel like writing it again. I got the bottom one. 0.30, very good. So 0.30 moles. All right. Is anything different about this than we've ever done before? We've just done it twice. Okay. Yes, it's aggravating. I understand. But there's no other way to do it than doing it this way. This is it. This is the only way we can do it. So now we've got moles of each compound. So what's our second step? Convert moles of the reactants, which we have, to the moles of the unknown. Now, if we go back and look at our problem, what is our unknown? NaNO3, right? So how do I go from mole of one to mole of something else? That's the easy part, right? So, oh, that's the wrong button. Why would we use the bottom one? All right, remember, got to convert this first before we can find the limiting reactant, okay? You got to do both steps before you can find that. One way. Okay. All right, so we've got moles of the bottom one, and I'm just going to write moles of NaNO3 on top so I know where I'm going, because I know what's on the bottom. And I know I'm shorthanding this, but this is just for speed. All right, so this is mole to mole. Where does mole to mole come from? Coefficients. All right, so on the top one, what is your top to bottom ratio? 3 to 3. And again, if you're not quite sure where that came from, this number came from here. This number came all the way over here. All right, what's the bottom ratio? 3 to 1. Very good. So bottom again came from there. This one came from right there. And I know there's a bunch of lines messing everything up. So now we can run these numbers. Do you have to do anything to the top at all? Why not? 3's cancels out, so there's no reason to even have to do the calculator. So we know that it's going to be 0.37 moles of NaNO3. And then on the bottom one, you should be able to do that in your head. What is it? 0.9. 0.3 times 3 is 0.90 moles of NaNO3. Okay, so let's look at it this from two perspectives. I'm going to let y'all finish right before I start talking. Let's pretend that this was two separate problems. Problem A, I have 30 grams of ammonium nitrate. How many grams of sodium nitrate can I make? What if that was a problem? What would your answer be? Started with ammonium nitrate, 30 grams. How many moles of sodium nitrate can I make? 0.37, right? Totally separate problem. The very next day, I say, you got 50 grams of sodium phosphate, which is right here. How many moles of sodium nitrate could I have? I could have 0.9. But what's the problem when today we have only those two amounts? The most you can make, least that is produced. I know that's weird, but if you think about it, you're like, all right, well, I know that 0.37 is the least amount. Well, isn't that going to be the most that I can make? So that tells me right here. And if you go back and look at our last step, the least number is the limiting reactant. But again, here's the problem every year that I have. People want to take this thing and say that's the LR. Why can that not be the LR by name? Because what is NaNO3? It's a product. How can a product be a reactant? It can't be. But so where did this come from? It came from way over here, which tells me what about this thing? This is my limiting reactant. So y'all see how that works? Haley, you with me? Sure? You kind of got... Everybody's sure they're with me. All right. Now, so I know for a fact that this right here, that the 30... Try that again. That the 30 grams of ammonium nitrate is going to limit my reaction. But I still haven't really answered the question, because what was the actual final question? What is the mass? But what's the great news? What can I do with this number right there? Convert it to grams. It's a one-step mole to gram conversion. So go ahead and run that for me real quick while I take care of this. Okay, put that on my cart. You'll actually see it's on this side of the basket mats. It's kind of right there in the middle. Just sit on top of this. Thanks for bringing that by. Anybody? Sounds right. Did you do 22.99? Did you do 22.99 for sodium? That's fine. What did you get? 84.99. I mean, it's only going to go up 1 or 2 decimal places. It'll be fine. Do what? Matter of fact, I think when I did it earlier, it came out to be 85 on dot. I mean, there's not really a big difference. Because if you do 0.99, I really think it is 85 on the dot. I remember that number from earlier. Okay, so this is just an easy one-step conversion. So 0.37 moles times, if you make it easier, you can do 85. What'd you come up with? Let's go 2 sig figs. So 32. 31.5. Oh, okay, gotcha. All right, so just 31. So 31 grams of sodium nitrate. So in this part of the little chapter that we're working on, the limiting reactant, nothing is different. Nothing at all. The only part that is changed is that we have to do it twice to determine our limiting reactant. Yes, it's another step. Yes, it's more math. Yes, it's more of a chance to mess up. But this is the only way to do it. And it's the easiest way to do it. You can find any YouTube video out there and try to watch how they do it, and I can guarantee you they're not going to make it any easier than this. Okay? This is the easiest way to do it. Any questions? Matter of fact, I would love for you to find an easier way to do it. Love that. Because I'm open to change. Yes, this is the limiting reactant right here. Is there a reason that you asked that? I'm kind of... Okay, yes, that is the limiting reactant. Any other questions? Right, let's do one more and we'll call it in for the day. No. And like I said, we'll do excess Monday, and we'll do... Matter of fact, for some reason, I don't even know why they gave you this question. What? It is, isn't it? Forgot about that. You can't even do a percent yield on these questions because there's a piece of information missing that they have to give you. You cannot find the percent yield on these questions because percent yield is actual over theoretical. What we just found was in theory I could make 31 grams. Actual was, this is my lab, this is what I've done, and I actually made whatever. So what you find in this is the theoretical, is numbers on paper. No, you can actually do it. They didn't give you the numbers. Like it would say at the very end of the say, and from a lab, blah 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 was actually produced. So then you just plug your numbers in and go. Okay, last one. First of all, balance. Don't say anything out loud. Give everybody a chance to balance. All right, what you got? Okay. 3, 2, 1, 1. All right. Now, this is going to be a little bit aggravating too, just because of how big the compounds are and how nasty the masses get. But that's just part of it. So, answer the question at the top of the sheet. Assuming that we start with 100 grams of calcium carbonate. What is calcium carbonate up here? It's the first one. You've got to recognize that. Now, I'm actually going to add a decimal point behind it to make it 3 sig figs. And then, and 45 grams of iron 3 phosphate. What's iron 3 phosphate up here? The second one, very good. So making sure that you understand that is very important. So we've got 45 grams of this. Now, you guys get to have some say on this one. Which product do you want to convert to? I don't care. How many of them do calcium phosphate? Iron carbonate. We have 2 minutes. 3 people. All right, we'll go to that one. I guess you really don't care. Both of them. All right, so we're going to convert to iron 3 carbonate. Doesn't matter. I mean, I could pick the other one and we can go to it. We're just going to pick one instead of having to do both of them. All right, so again, the same problem starts off. Which number do I pick to go to my product? Do I pick calcium carbonate or do I pick iron 3 phosphate? Do I pick 45 because it's the lowest? What do you have to find first? What do you have to find first? The limiting reactant. All right, so let's start there. So my first step is convert grams to moles. So I've got 100 grams of CaCO3. I've got, and I think it's actually 100 on the dot for calcium carbonate. Thank you, sir. That's exactly what it is. 100.09. And guys, I'm leaving the compounds out just for making this go a little faster. And then 45 grams of FePO4. 100.9. Nick, did you get the other one? Yeah, excuse me, 100.09. 55.85 plus 30.97 plus 16 times 4 gives me 150.82. 150.82. And that's going to give me moles. All right, so looking up there at the first one, you're going to be like, wait a minute, hold on, shouldn't that be 1? And if you divide it, you actually get 0.999 moles of CaCO3. Bottom one comes out to be 0. I'm going to go to 3 sig figs, even though you technically only really need 2. It's just going to make it a little bit more accurate. Alright, here's where I have a feeling, and since y'all kind of jumped on this bandwagon a little bit earlier, it scares me from this point you're going to stop, and you're going to say that iron 3 phosphate is the limiting reactant. But you've got to remember, there's a second step we have to do before you can pick your limiting reactant. You can't just go based on the mole-to-mole comparison. You got to go one more step. What do I do next? My mole-to-mole, I got to convert it to my product. Very good. So I'm going to take these numbers, and I'm going to convert them to the product. So mole of CaCO3 is going to go to mole of Fe2CO3. I know that's a long, aggravating one. CaCO3 going to mole of Fe2CO3. Okay. I want you to practice this. Plug in your mole-to-mole, come up with the answers, and label and identify the limiting reactant. Yes, ma'am. Sorry. Yep. What I did is I wrote the wrong reactant compound. FePO4. Thank you. So like I said, so run your numbers, get an answer, and identify the limiting reactant. Alright, so what'd you get for the mole-to-mole on the top one? Hang on, no, the mole-to-mole. 1, come on, Mr. Penn. 1/3. What about the mole-to-mole on the bottom? 1/2. Alright, so what was your number of moles on the top one? 0.333. You didn't even really need a calculator on that one, did you? Alright, moles of Fe2CO3, and the bottom one was what? 0.149. Moles of Fe2CO3. Alright, so from this point, we can now determine our limiting reactant. Who is it? Very good. It is FePO4. So this guy right here is going to be our limiting reactant. Now, it just so happens that the lower number in the beginning was our limiting reactant. Guys, it won't always be that way. Yes, 45 is less than 100, but you can't assume, because it's like I told you day one. You cannot compare grams. Matter of fact, up there on the top one, what was the limiting reactant? No, it wasn't. It was the smaller one. And the first one we did, the 30 grams is less than 50, and the 30 grams was the limiting reactant. Oh, yeah, that's right. Okay. And that's a matter of fact. Well, I've already erased it all, and I wish I would have brought that point up. Hold on 1 second. All right. So, is there a question about this? Okay. Hold on 1 second. So here's the deal. So we've determined our limiting reactant, and so what we're going to do is, can I stop and say I'm finished? No, because the question said I need grams. But here's the deal. Which one do I pick? Do I pick the 0.33 or the 0.149? I pick the least number. And so let's go one more step. So I've got 0.149 moles of that thing. I'm just going to put X because I'm tired of writing it. So we can go mole of X to gram of X, and obviously X is this thing. Okay, and now we've got to get a mass, and that thing is going to be aggravating to get. So, thank you. That's easy. What is it? 291.72. But before I move on, I want to make sure that everybody can figure this out real quick. How many irons are there? How many carbons are there? And how many oxygens? Not 6. There are 9 oxygens. Why are there 9? Because it's a distributive property, not an additive property. Okay? Please make sure that you get the 9, not the 6, because that's where some other people may mess up as well. All right, Nick, what's your final answer? 43.5 grams of X. But obviously X is iron 3 carbonate. Yes, sir. Yeah. Is she checking out? Okay. All right, any questions? Fantastic. That's it.